the metric system. So they give us some French there. I'm not good at French. Système International de Vitesse. You got to turn off the sound.
Yep, I didn't realize that. There you go.
Okay, so that's the long term for the metric system. It's the formal name. It's in French, whatever.
Okay.
Now the units you'll see on this prefix layout. It goes powers of 10. So I give you the powers of 10 as a number, and then as an exponent, and then the prefix, and then the abbreviation for the prefix. And in the middle, you'll see unit. And there's 3 common units for mass, which is the gram, for length, which is the meter, and for liquid volume, which is the liter. Although it could, just volume in general, the liter. Now, in some respects, they'll use the kiloliter, or not the kilogram. A kilogram is about 2.2 pounds. Kilo means 1,000, so it's 1,000 grams. A gram is really small. You know, I think a pencil eraser might be a gram. But that's your basic unit as far as this goes. Now, in shipping and manufacturing, they use kilograms because it's more like 2 pounds. 2.2 pounds to be exact. Anyway, the commonly used unit to measure length is the meter. That's about 39 inches. A door is about 2 meters high. A door is 80 inches. Standard door, 6'8", 80 inches. So that's about 2 meters. And it's about a meter wide. A typical door is about a meter by 2 meters square. So that's the length we use as a meter. Commonly used to measure mass. See, now they don't list the gram here. So what they're trying to get you to understand is the kilogram is a commonly used unit. It's not really the unit. It's just that's what we use a lot when we're talking in terms of larger packages, larger things. And the liquid volume is the liter. A liter's a little bit bigger than a quart. It's about 33.5 ounces. Or maybe a little bit bigger than that, maybe 34. Anyway, I remember traveling. There's people that refer to the imperial gallon, which is 4 liters. So they call it imperial gallon because it's larger than an American gallon, which is 4 quarts. And the measure of temperature is degrees Celsius. You'll see it's C with a degree symbol. Now, in the old lingo, when I was in college, like a chemistry class in the, dare I say, the 60s, it was called centigrade, meaning 100 degrees. Centigrade, gradients. So 100 gradients, 100 degrees. Because the scale goes from 0 at freezing to 100 at boiling. So it's 100 degrees. So it's a centigrade scale. But about 30, 40 years ago, they decided to honor some French guy named Celsius. So they changed the C from centigrade to Celsius. Sometimes I slip. I still say centigrade, although it's getting less and less common for me to do that. Anyway, that's where it came from. It's just some guy's name. But originally, it was 100 degrees. And we'll get into that as we go forward too. In the metric system, it's always powers of 10. The digits don't change, right? It's what changes is the decimal place. And you see I have some directions there for how to move the decimal place. When you go up from one measure to another, you divide. When you go down, you multiply. And all that means is moving the decimal place. Each power of 10 is one decimal place, right? Okay. So 10 times the base unit, if you just look at it, it's deca. Now, there's two different ways to write it, capital D or lowercase da. I don't like the lowercase. When you see it, know what it means, but I prefer the capital D because it's one letter. It's just simpler to write. So deca. And then if you go 1/10, if you go down one, you'll see it's deci, like decimal, deci. Now those two aren't used a lot. The ones that are used a lot are mega, kilo, centi, and milli, and micro. You might hear nano and like giga now, gigabits, terabytes, right? You'll hear those. Because now with the miniaturization, computerization and stuff, everything's small packages. Thousand, both of those are used, kilo and milli. So if you go up three powers of 10, 3 decimal places, it's kilo. And kilo itself has the designation of 1,000 grams. People don't even say kilogram anymore; they go kilo, right? So a kilo means 1,000, and milli means 1/1,000. Although a millipede has 1,000 legs, right? Or is that a centipede? I forget. All right. So freezing point, I think I just mentioned that. Freezing point is 0 degrees Celsius. You can see the distractors. You can't pick 32 degrees Fahrenheit because that's not in the metric system. It is a freezing point of water, but it's in the American system. Right. So the only one that really only makes sense is 0 degrees Celsius. And then the boiling point is 100 degrees Celsius. You can see the distractors. In Fahrenheit, it's 212. Because you know that the temperature scale is totally arbitrary, right? We'll talk about that on Thursday. Because the temperature scale is just a large evacuated bulb, glass bulb. At the bottom, there's mercury. And depending on the temperature, the pressure inside here changes. And since it's a constant volume, Boyle's law takes place. I think it's Boyle's or the Charles law, one or the other. The lower the temperature, the higher the pressure, and this stays down. The higher the temperature, the less pressure, and then this rises. So when you're at the freezing point of water, it rises to this height. And if you mark it here and you mark it 0 degrees Celsius, then that's your freezing point for the thermometer. Although if you want to sell them to Americans, then you write 32 degrees here Fahrenheit. But it's just a mark on the glass tube. And then if you put the glass tube in boiling water, then this becomes 100 degrees Celsius. Because now this is boiling, this rises up to here. And on the other hand, if you were selling it to Americans, you would write 212 degrees Fahrenheit. So you'll see how we can make a linear relationship between the two scales, F and C, and come up with formulas. But they're just arbitrary scales because there's no true zero. It's just arbitrary. And the normal body temperature. 37, you got it. So you could say 37 is approximately 98 degrees Fahrenheit, right? Okay. We'll get into that some more. Number We'll skip some of these. Number 19. Some of these are also homework ones, so I'm not going. So without referring to any of the tables or your notes, give the symbol and equivalent in liters for the unit deciliter. So the symbol is DL, lowercase d. And they'll use a script L, in the computer. We use a capital L for liter. The script, you know what I mean by script L? They'll write just like that. Liter is like that. But we'll write L like that. As soon as then there's no confusion. Okay. I think they'll accept it here. Yeah, they accept it here also. But we can't really put a script L in there. The equivalent of 1 deciliter in liters. So see, if I'm going from deciliters, this is where you just go up. From deci, you're going up, so you move the decimal to the left. So it's 1/10 of a liter. Right? See, that's what the D means. The D means 1/10. So if I write DL, what I'm really saying is 1/10 liter, but we don't say 1/10 liter, we say deciliter. And that's what the D on this table says. You can see for a D, it's 10 to the minus 1 or 0.1. And if you remember your numbers, those are all equivalent ways of writing 1/10, right? A negative exponent means take the exponent across the division line and make it positive. So those are all 1/10. That's so now we have a new one. D, lowercase d, means 1/10. Okay, that's all. That's what's going on here. Number 23. Without referring, give the symbol and equivalent in liters for the unit deciliter. So now we're going up. So we would write capital D, capital L. Let's see if they accept it. Now, you know what they want? Luckily, we have another chance. They want DA. Okay. Now, we have to conform to what they want. That's why we have an extra chance to do that. But if we were writing it out, we just write capital D. It's just a little bit easier. Now, if we're going up, we multiply. So this will be 10 liters. Because that's what DA means. It means 10. Follow? And if you look at the table, next to DA, the power of 10, 10 to the first. So. And now you're going to notice here that the numbers don't change. It's going to be 17 with which of some zeros. So from meters to millimeters, I'm going down 3 spaces. That means I need 3 zeros. I got to multiply by 1,000, so it's 17,000 millimeters. See how that works?
Yeah.
You got to remember whether you're going up or down. See, the 17 doesn't change. All it changes is where the decimal place is. Because this means 1 over 1,000. And so if I put 1 over 1,000 in here, I would cancel the 3 zeros, and I would cancel, and the M would cancel, I would have 17 meters. See, they're just, it's like numerical equivalents written with letters. That's what it means. But I hope this table helps you,
It does, yeah.
because otherwise, if you try to do it in your head, you might get confused. But you got to have, if you have somewhere to go to. Okay, here's a DAM. We want to know how many meters that is. So you see, we're at DA, so we're going down. So we're going to multiply. So the answer is 40, right? Because the DA means 10, so 4 times 10 is 40 meters. Now, they don't have meters out there. What they're asking for is what goes into the blank.
Right.
The meters is there. So if you just think of that as 10, 4 times 10 gives you 40 meters. The DA vanished because I put a 10 in there, but the meters didn't vanish. Okay, 31, 241.3 centimeters. So now I'm going up. I'm going up from centimeters to meters. 2 powers of 10. So I got to move the decimal place 2 places to the left. So this will be 2.413. See what I mean about the digits? The digits don't change. Now in the American system, they change all the time because you don't have a 10 for 1. You have a 3 for 1, a 12 for 1, a 5,280 for 1. You have all kind of strange turnovers, you know.
Yeah.
But in the metric, all you're doing is moving the powers of 10. But I like that in a way. Some people don't. See, there's your script L. See? So, you know, okay, number 32. So now we're going milliliters, we're going up. So once again, we're going to divide. So we need to move the decimal place 3 places to the left, so I need 2 zeros in front of the 4. You see how I moved the decimal place 3 places to the left, so I need 2 zeros there.
Right.
Okay, am I going too fast?
No.
No, okay. That's 32, 33, 4.8 kilometers to millimeters. This is going to be a huge number. We're going down 6. We need 6. We've got to move the decimal place 6 places to the right. So I need 5 zeros after the 8. Because there's 1 decimal place, and I need 5 more. See, if you go from kilometers to millimeters, you're going from 10 cubed to 10 to the minus 3. That's 6 powers of 10.
Right.
So I need a 6 decimal place. So it's 4.8 million millimeters.
Wow.
I know. Well, the nice thing about the metric system is you use the right prefix for the system that you're in. You know, and then all you really do, like you wouldn't want to use millimeters for something that was 4.8 kilometers long. This is too big of a number. So what, you know, if you're in the microscope, you would start using, you know, nano and pico and stuff like that because it would make more sense. All right, so let's jump to 42. Let's see what's going on there. Okay, this one got a whole bunch of numbers in it. We just have to pick out the correct number and make the change. So they give some particulars about some particular measurements about a species of jellyfish, how long its diameter, its tentacle length, its weight, and its travel speed. So what's the length of the specimen's tentacles in kilometers? Well, right now, they gave it to us in meters per second. Oh, I'm sorry, length. They gave it to us in meters, yeah. They want to go from meters to kilometers. We're going to go up 3 places. So we got to move the decimal point 3 places to the left. So it'll be 0.00136. See, the 136 doesn't vanish. All the changes is I move the decimal place.
Wouldn't it be the 21 meters? Because the tentacles that are 21 meters long?
Oh, it's tentacles.
Yep, so 21 meters.
Oh, I saw tentacles and meters, and I put those 2 together. Okay, so what's the correct answer? Using 21.
0.021.
Yeah. I still need 3 decimal places. Now it's unwritten because it's to the right of the 1, so 1, 2, I need a 0. Thank you. I just didn't, my line of eyesight wasn't good. 43. So it's the same idea, but there's different numbers now. Same kind of problem. The weight. Okay, so the weight's given in kilograms, and we're going to grams. So once again, we go down 3 spaces. 3 powers of 10, I should say. So I need 3 zeros. So it's 136,000 grams. 136 kilograms. That's like 275 pounds.
Wow.
Because it's 2.2 pounds per kilogram. If you look on here, a lot of these I remember.
That's a big jellyfish.
Yeah, I'll say.
Yeah.
275.
Bigger than I am.
I wouldn't want to run into him or her.
You know, swallow me whole.
So here's a weight in decigrams. So now we're going to take kilograms to decigrams. We're only going to go down 2. I'm sorry, 4.
Right.
So I need so that's 185. Yeah, it's still a lot. I need 4. Okay, and then 45, probably the same thing. Yeah, a bit tired of this. See, now this one's the speed. This is meters per second. We went decimeters per second.
It's 1.17 meters per second, and then deci would be.
Go down 1, so you multiply by 10. So move a decimal place 1 place to the right because you're multiplying.
So it's 1 point.
So 11.7. We have 1.17. Move it to the decimal place to the right one space.
Okay.
So it becomes 11.7. All right, one more of these, I think. Yeah, one more. So now it's in kilometers per second. So now we go the other way. See, it's meters per second, which makes sense. But kilometers per second, I need three decimal places to the left. So I need 2 zeros. But you see, once again, this is just for academic purposes. This doesn't make any sense in real life unless you're comparing it to a car or something, for comparison purposes. Because this one makes more sense because you right away know, well, that's about a little bit over 4 feet per second. Okay. All right. So okay, now I'm not sure why people have difficulty with these, but I can do this one on the board. The thing of it is you have to give your answer in the original dimensions, not in what we changed it. So 1.1 kiloliters, 900 liters, and 10,300 deciliters. So I would change them all to liters.
Right.
So this is 3 decimal places to the right because you're going down 3 spaces. This one you're going up 20. So you divide. So this is the smallest, this is the second, and this is the third. So 1, 2. Because you have to report your answer in terms of those.
So it would be A, right?
Yeah, it looks like A.
Wait a minute, so that's 1.1. Oh, yeah.
Yeah, I think it's A. Okay? So usually they have one of them as a unit. I mean, you can change them all to kiloliters and try that on for size. Should we do that? So this is 0.9 kiloliters. And I go up 4, this will be 1.03 kiloliters. So once again, 1, 2, 3. You could, I mean, I would go to the unit because it's just because then you're always it's easier. Right?
Yeah, it makes sense.
Okay, so that was 49, 55. You'll have at least one of those. Okay, so this one's straightforward. It says one pump removes 1 deciliter of water per minute, and another pump removes 1 deciliter of water per minute. You just have to make up your mind which one's larger. Which pumps water faster? Well, which volume's larger? It'd be the deciliter. So it'd be the pump that removes 1 deciliter per minute because 1 deciliter is greater than 1 deciliter.
Okay.
In fact, it's 100 times bigger.
Right.
Because it's two powers of 10 different. Make sense?
Mm-hmm.
Okay. And then number 60. Okay, painting, including the frame, measures 89 centimeters by 58 centimeters. Okay, how many centimeters of framing were needed to frame the painting? Which geometrical, and this is not a perfect scenario because they're forgetting about how wide the frame is and how far it extends. We're just using those numbers as an academic exercise. So I really don't like this problem, but so anyway, which geometric idea are we needing for the frame? You have a rectangle, right?
Mm-hmm. Yeah.
It's the area that we're talking about.
Area is what's in the middle. The frame isn't in the middle. The frame is around the outside. What do we call that? Perimeter. So if you just take the sum of those and multiply by 2, because you've got 2 lengths and 2 widths. So we would just go 2 times 89 plus 58. That'll give us the perimeter, without considering the width of the frame, because obviously there's corners above and below, and so, but they're not considering that. It's a, it's an idealized situation. So but once you understand that it's the perimeter, and then they just want to know how many millimeters. So from centimeters to millimeters, I go down, so I multiply it by 10, I need a 0, so 2940. In real life, I would have to figure out the width of the framing material, and then I would need double that for each side, because I'm going to put a 45, and then I would have to add a little bit more for waste.
Or you can just bring it to a frame store.
Yeah.
Can you frame this for me?
You guys don't know this, because see, my wife is a fine artist, and I make frames for her.
Do you really?
Yeah.
That is awesome.
Yeah.
Yes.
Yeah, she's.
Makes sense on why you got into that question a little bit, though.
A little bit.
Yeah.
All right, so I think that's pretty much, most of these are homework problems. We could try this one. I don't know if this is a homework problem or not. I don't think so, but just to give you an idea of what else we could do here. Convert to an appropriate metric unit so that the numerical expression in the given measure does not contain any zeros. So if I had 100 millimeters, how could I write that as 1 something? If I'm going to move the decimal place 2 places to the left, that means I got to go up. 2 spaces from milli would be deci, so it would be 1 decimeter. All right, because deci means 1 1/10. Milli means 1/1000. So you can play with the numbers forever. We'll just leave it go. I think we did enough on that. We're going to go to section 7.2 now, which is length, area, and volume. I think there's more in this one that we need to do. Hectares, abbreviated HA, is a unit of area, metric area. I gave it away. There's 2.5 acres per hectare. I think that's on the conversion. Acres is the American system. If you look at area, you'll see 1 acre is 2/5, 4/10 of a hectare. So you can always do these both directions. You'll see that what these do is these crossovers give us a what we call a unit fraction. So we have 1 acre equals 0.4 hectare. So that's 2/5, right? 0.4. If I multiply both sides by 5/2, see now I have a different unit formula. I have 2.5 acres equals 1 hectare. See, here the unit, I'm focusing on the acre, here I'm focusing on a hectare. So, but they're still the same, they're equal. And when we do use the unit formula, it doesn't matter which way we do it, as long as we have unit fraction, one or the other. But anyway, hectares is area. I like to think of it as 2.5 times larger than an acre because, you know, I remember I remember the lot that we lived on was 1/3 of an acre, my family house. So I get a better idea of what that means. Number 7. Cubic centimeters are a measure of the exponent gives it away, and the word cubic. When you think of a cubic centimeter, you think of a cube. It's got 1 centimeter on each dimension, length, width, height. So 1 times 1 times 1 is 1. Centimeter times centimeter times centimeter is centimeter cubed. So it's a measure of volume. Okay. What's really neat is 1 cubic centimeter, which is otherwise known as 1 cc, is also 1 milliliter for water and other substances that have a density close to water. Okay, and the other thing that's neat is that, so you got volume of a solid, of potential solid equals the volume of liquid. For water, it also weighs 1 gram. And that's on the top one, equivalence. See, 1 centimeter cubed equals 1 milliliter equals 1 gram, which is nice for water. That's another reason the metric system is nice, but for chemistry laboratories. That's a perfect relationship. Now, it's not going to work for gold because gold's so dense, but you know, for any liquid that has water as a base, it's pretty close. Let's see, number 17. The distance between the 2 mountaintops. Which one would you use? You think of mountaintops, they're pretty far apart.
Right.
So would you use centimeters?
No.
Meters? Millimeters?
No.
Would you use kilometers?
Kilometers.
Yeah, kilometers. Kilometer is about 0.6 of a mile. In fact, well, there's 1.6 kilometers per mile, or 0.6 of a mile equals 1 kilometer. I don't know why I remember these stupid things, but I remember.
I'm glad you do.
That's what my
You're doing it so long, yep.
22. Cup of coffee is about how wide? So these are all 8s. Now, there's 2.5 centimeters per inch. So 8 centimeters is 3 inches. 3 inches for a coffee cup? 3 inches wide.
Oh.
Wide. It's about right.
Yeah, my coffee cup is actually 3 times the size of that, but
Well,
that makes sense.
8 millimeters is too small.
Right.
And 8 decimeters,
It's too small.
too big.
I mean, too big, yeah.
Yeah. Okay, so 8 centimeters. 9 times out of 10, the centimeters is the answer to this. So remember that. 23. A cruise ship's about how high? Would you measure centimeters?
No.
Kilometers? 92 kilometers?
No,
Well, 92 meters. That's about 100 yards. It's about 300 feet. That's pretty, yeah. Well, if they're talking about going up to the top of the smokestacks, yeah, that's pretty. I don't even know if they have smokestacks anymore. I've never been on a cruise, so I don't know.
Since graduation, that's a present for myself.
Yeah.
Yeah.
The width of a ruler. Now remember, centimeters, there's 2.5 centimeters per inch. So that would be about 1.5 inches for a ruler, 4 centimeters. Because 4 meters is too big and 4 millimeters is too small. So 4 centimeters. Oh well, we're getting really grilled in centimeters. See, 31, we'll leave some of these behind. Okay, this is for square. Indicate the unit of measurement for a blackboard, for a whiteboard. What will we measure this in? We can eliminate the second and the third one because they're cubic.
Right.
So will you square meters or square kilometers?
Meters.
I mean, we could use either one, but the one that makes sense is the meters. So this would be about 1.5 meters by about
3 meters maybe?
2.5 meters. Because if a door is 2 meters, yeah, maybe it's 2 meters. 1.5 meters by 2 meters, I don't know. But we use meters, because they only want square meters. 35. Indicate the metric unit measurement you would use to express the area of a folded paper napkin.
Centimeters?
Square centimeters, right? See, here's a folded napkin. Which one can we eliminate? Cubic centimeters, right?
Mm-hmm.
We can eliminate square kilometers and square meters.
Definitely.
We could, if we had to choose between B and D, we would choose square centimeters. So square centimeters. See what I mean about the centimeters? They come up a lot. I don't know why, but they do. What's the approximate area of a foot tile? So I think what they mean is 12 inches by 12 inches. And since there's 2.5 centimeters per inch, that's about 30 centimeters for 12 inches, so it'd be 30 times 30. So it'll be about 900 centimeters squared. So A, first one. We don't want to use kilometers, and millimeters is too small again.
That would have to be like functional.
So it's centimeters again. I'm biased for centimeters. I don't know about you guys. What's the approximate area of a postage stamp?
So, yeah.
We can eliminate A.
Yes, of course.
That would be definite.
Yeah.
Now, I said that there's 2.5 centimeters per inch, so that's, well, let's see, no, that's what centimeters squared.
That's, yeah.
I think it's B again. Right, because millimeters is kind of small.
Very small.
When you look at it, well, if there's 2.5 centimeters per inch, there's 25 millimeters per inch. And if this is 5 millimeters squared, to get to 5, to get to 5, you'd have to have the square root of 5 if it was a square. That would give you 5 meters squared, but the square root of 5 is like, it's about 2. It's between 2 and 3, so let's call it 2.5. So 2.5 millimeters. 1/10 of an inch. See, I'm going through the equivalences in my head. 1/10 of an inch is just really small. 1/8 of an inch is just really narrow, you know. And there's no postage stamp that small. So it has to be centimeters. Again. Okay, I guess it's one of those things that's like, you guys have taken statistics?
Not yet, no.
Not yet.
Okay, when you flip a coin, assuming it's a fair coin, in other words, it's not weighted or loaded or doesn't have 2 heads. If you get 7 heads in a row, the next throw of the die is still 50-50, unless you can prove otherwise. It just so happened I've got 7 in a row, but the law of large numbers tells us that if we keep flipping it 1,000 times, we're going to get close to 50-50. It's just that at some point, there might be 7 heads in a row, there might be 8 tails in a row at some point, but overall they even out. Law of large numbers is what it's called. So I'm not sure why I started. Oh, because some people would think, well, since we use centimeters so much, we're bound to like stop using centimeters, but
Not always,
not always.
except for the next question.
Yeah, except for the next. Let's get away from these, I hope. Let's see. Determine the metric unit that would best express the volume of a pot of coffee. So a pot of coffee is about a quart, right? So which one would be, would you use cubics? You wouldn't use cubic kilometers or cubic meters. So would you use cc's or cubic millimeters? Once again, cc's, cubic centimeters. You can think of a centimeter as about a half inch. There's 2.5 centimeters per inch, so it's actually 4/10 of an inch, but you could just round it off to say it's close, a little bit less than half an inch. Uh, 55. Determine the metric unit which best used to measure the volume of a truckload of ready mixed concrete. Now, concrete comes in cubic yards. That's how you've heard the expression the whole 9 yards, because a concrete truck, those ones that spin, they carry approximately 9 cubic yards. So when they say the whole 9 yards, that means you want the whole truck. Because I don't know if you know this, but there's 2 things that happen with the truck. They either know ahead of time that they're going to take half a load to one place and then the remainder to another place, provided they have the same type of mixture, because each concrete mixture is slightly different depending on what you're using it for. Walls are different than floors, are different than ceilings, blah, blah, blah. A lot of times what happens is you might see cement, there's places where cement trucks go to dump the end of a load, because if they only pump 7.5 yards, they got to go dump the rest before they go back to the shop. So they have places where they dump it, or if you know that somebody who works at the plant, like a dispatcher or somebody that's in your church or something, you need concrete. They'll say, okay, we'll give you whatever we got left over.
Oh, okay.
Just be ready for us at a certain time. Anyway, yeah. But anyway, what will we measure it in? We wouldn't measure it in distance, length, which is kilometers or meters. We wouldn't measure it in cubic millimeters, so it's got to be cubic meters. Since a meter is a little bit bigger than 3 feet, it's about the size of a yard. So you probably have about 8 or 9 cubic meters in a cement truck. If you think of a cubic meter as like, well, a cubic yard is 3 foot on the side. So the difference between a cubic meter and a cubic yard is it's 39 inches instead of 36. I think it's 39. Let's see if that's right. Yeah, 1 yard is 0.91 meters. So let's see for the cubic, the volume. See, there it is. 1 cubic yard is 0.765 cubic meters. It's the last one under volume on the conversion table. So it's about 3/4. So a cubic meter is about 3/4. A cubic yard is about 3/4 of a cubic meter. So yeah, it'd be about a little bit less than 7 cubic yards would fill up a concrete truck. Important stuff you're learning here, you know.
Yep, I see. I'm using this every day for the rest of my life.
All right, here we go. We need to calculate this. It says a cubic or a cardboard box, yeah, is 52 centimeters long, 63 centimeters wide, 65 centimeters tall, and all the dimensions are the same. if any one of these wasn't a centimeter, I'd have to make a change. Because I'm gonna get centimeters cubed, but only provided these are all centimeters. So I don't need to worry, I just go ahead and take 52. Oh, they want it estimated first, I didn't read it. It says round all the numbers to the nearest 10, so the 52 becomes a 50, the 63 becomes a 60, and the 65 becomes a 70, right? The round off rule is the 5 makes that a 7. So the approximation would be 210,000 cubic centimeters. Now they want the actual volume. So 52 times 63 times 65 should be less. No, it's more. 212, 940. Pretty close. Okay. Number 67, they want us to do estimate the volume of oil in the barrel in metric units by rounding the diameter to the nearest meter and using 3 for pi. So the volume is pi r squared h. So we don't have to round the height, but we're going to say pi is 3, r is, we round it to the nearest meter, so that'll be 2 squared. And then the height is also 2. So it's 8 times 4, that's 24. So 24 meters cubic meters. Oh, oops, I did something wrong there. What did I do wrong?
Oh, you did one squared and the other one not squared?
Well, h is not squared. Oh, it's diameter. See, it's, but we don't want the diameter, do we? We want the radius. So it's half of 2. So it's 1. So it's 6 cubic meters. See what I did wrong? It says the diameter is 1.7, but the formula uses r, which is d over 2, right? D equals 2r. So if we round d to 2, then r is 1, if we round it. Now, in the next one, we're going to get the actual. So for the actual, they say, well, we don't need a round, we just go like this, pi times r. So I'm going to do it this way, 1.7 divided by 2. There's r squared. There's r squared times the height is also 2. So to round it to 2 decimal places, it'll be 4.54. Okay, any questions about that one? Sorry, I screwed it up at first there. I saw the number, and I just used the number for R, but it's the number 1.7 is for D. So in the second formula here, I got pi, I wrote R what it is, D over 2. That's R squared times H is 2. And then just round it to the nearest second place. All right, next one, 69. 1 liter of liquid has the equivalent volume of as a guess. It wouldn't be a cubic meter, would it? And it wouldn't be a cubic centimeter.
I thought it was yeah, the decimeter.
All right, so it's on here. See on the front? Find the volume 1 liter. And then go to the left, and you see 1 decimeter cubed, which is 1 cubic decimeter. All right, so you don't have to, I mean, that one was easy to reason out, but if you get stuck, most everything you need is on here. If it's not, you can add it, or you can use what you got to get the answer you need. 76. Let's see. What's this one? Another one of those roundings. Oh, we could do it. Approximate the area of a circle with the given radius. Use pi equals 3.14 and round the result to the 10th place. So use a equals pi r squared. You guys know about the hillbilly who went to the principal's office? So what are you teaching my kids here at school? The principal looked at him and says, I'm not sure what you're referring to, sir. So when my boy came home and he said, pi r squared. And the principal said, yeah, it must have been in geometry class, referring to the area of a circle. He said, I don't care about no area of a circle. He says, everybody knows pi r round, cornbread r square. I love that.
Oh my God.
That's a good math joke, isn't it?
Yes, it is. Yes, it is. I don't think I've ever heard a decent math joke, but that one I'm definitely good. Yeah, I like it.
Okay, so we use pi r squared. So they said use pi is 3.14, so I don't have to put in the exact value. And r squared, so it's times 1.3 squared. And round it to the nearest tenth, so 5.3 square meters. All right, so that was easy. Number 76. A house 32 meters by 9 meters is surrounded by a walkway 1.5 meters wide. So this one, we need a picture. So it's obviously a rectangular house, 32 by 9. And it's got a walkway around it. So this is 9, this is 32. And this is 1.5. All the way around. All four sides are 1.5. So the question is, the area of the region covered by the walkway and the sidewalk. So I need the outer dimensions. I need this dimension and this dimension. So can you see that this dimension is 9 plus 3? Because there's two sidewalks. And this one is 32 plus 3. Because it's got two sidewalks. So the total area of the house and the sidewalk is 12 times 35. 420 square meters. Now, they want to know the area of the walkway, the sidewalk. There's a real easy way to do this. Can you reason it out before I tell you? In other words, they want to know this area. It's a subtraction problem.
You have the area of the house and then subtract it from it.
Yeah, subtract the area of the house from 420. So it's 420 minus 9 times 32. In other words, I'm subtracting the white rectangle in the middle. So that leaves 132 for the shaded sidewalk. Make sense?
Mm-hmm.
Yay, we did it. Okay. Number 77. Mr. Hirschman has purchased a farm that is in the shape of a rectangle. So the dimensions of the piece of land are 2.2 kilometers by 2.02 kilometers. How many square kilometers did he buy? So he bought 2.2 times 2.02. Since they're both kilometers, I know it's square kilometers. Now notice they didn't tell us to round it. So we report all the decimals. 4.444. Then they're going to ask us, how many hectares did he purchase if 1 kilometer squared equals 100 hectares? All right, so in case it's confusing, I will now introduce the idea of dimensional analysis. So you can see how to do it. It's pretty straightforward. We have 4.44 square kilometers, and we're going to multiply by a unit fraction. We have 1 kilometer squared equals 100 hectares. So I want to cancel the kilometers. If these are equal, then I can divide both sides, or multiply, I can multiply both sides by this fraction because it's equal to 1. This is 1. It's a unit fraction, right? Mm-hmm. I could have done it either direction. The reason I did it this direction is because I want the kilometers downstairs so they cancel. See, this is just a unit because they're equal. So the kilometers cancel, so multiply by 100, so you get 444.4 hectares. That's dimensional analysis. You can always create a unit fraction. Because you notice on these, one of them is always equal to 1. Even if it weren't, it would still work. But it's easy because you just, I'll give you a real simple one. 12 inches equals 1 foot. My unit fractions, I got 2 of them. It's this is 1, or this is 1. Because it's the same thing divided by itself. Well, I can use either unit fraction. So if you said, well, how many inches in 3.5 feet? So I got 3.5 feet. So which one am I going to use? I'm going to use this one because that puts the feet in the denominator, and so it cancels. So there's my answer. Just multiply it out. And if I went the other way, and you said, well, how many feet are there in 27 inches? So I have 27 inches. So now I'm going to multiply by 1 foot, 12 inches. And now the inches cancel. And so now I divide 27 by 12, and my answer is in feet. So these are called unit fractions. Because when 2 things are equal, you can just set up a fraction. So for this one, we set it up this way. If we flip it, we still have a unit fraction. We could use it the other way. It all depends on what we want to cancel. So that's called dimensional analysis, and it always works. So what did we say? 444.4. Very good. All right. We'll do more dimensional analysis on Thursday because we'll be switching from one system to the other, for sure. How much larger is a square kilometer than a square hectometer? Well, how much larger is a kilometer than a hectometer? So from a kilometer, it's 1 power higher, so it's 10 times bigger, right? A kilometer is 10 times bigger than a hectometer. So for a square, it's 2-sided, so it's 10 times 10 bigger. So it's 100 times bigger. You follow? Let's see if I can. You have 1 kilometer equals 10 hectometers. So if I square both sides, I get 1 kilometer squared, right? Because the 1 squared is 1 kilometer squared. 10 squared is 100. Hectometer squared is so 1 kilometer squared equals 100. Right? Okay. And what if I did a cubic kilometer and a cubic hectometer? Then it would be 1,000 because it'd be 10 cubed. Yep. I think they might ask us something like that. We'll see. How many times larger is a square kilometer than a square decameter? Well, from a kilometer to a decameter is 2 powers of 10. So just for this plain measurement, it's 100, but 100 squared is 10,000. 10 to the 4th, right? 10,000. Well, if I just change this to decameter squared, then 100 squared is 10,000. So it's the same idea. I'm just putting a different equivalence in there. Because these two are equal that are in parentheses, and now I'm squaring them, so now these two are equal. When I get rid of the parentheses. All right? Good. You guys catch on pretty quick. That's good. Number 91. "17 centimeters squared equals how many meters squared?" So if I go up from centimeters to meters, I have to divide by 2. But I'm squaring it, so it has to be 4. So I need 0.0017. You see that? So that's reasoning it out. Now let's go ahead and use dimensional analysis. Can we know that we got 17 centimeters squared? We want to change it to meters. So we know that there's 100 centimeters equals 1 meter, right? So 10,000 centimeters squared equals 1 meter squared if I square both sides. So there's my unit fraction. I want centimeters in the denominator, centimeters squared, meters squared in the numerator. You can see that's why I moved the decimal place for it. I divided by. So you can always start with something that's true that you know as a unit fraction, and then just use it. Because if you try to do it in your head, you might get lost. So this is a much surefire way to get to the correct answer, because that's what we're interested in, is maximizing the points, getting to the correct answer. Does that make sense? Okay. That was 91. Number 93. We're coming in for a landing. 19 meters cubed to centimeters cubed. So let's do this one. So this is 19 meters cubed equals how many centimeters cubed? So this will be 1 million, right, if I cube it. Right, if I cube this, I get 10 to the 6th. 1, 2, 3, 4, 5, 6. So if I want centimeters cubed, then that'll be 1 million over 1 meter cubed, which cancels. So it's 19 million cubic centimeters. See, because we're going down, that's why we're multiplying. But we're multiplying by 3 times what we would normally multiply for the distance. The distance would have been 10 squared, so now it's 10 to the 6th. So I need 6 zeros. Make sense? Okay. 97. We just go to the table for this. 264 kiloliters. So find kiloliter. It's on the bottom middle. And they're equivalent. 1 kiloliter equals 1 cubic meter. So this is a 1 to, oh, I'm sorry, they have the table right in front of me. So it's 264. It's a 1 to 1. Correct?
Yeah.
Good. Easy. I like these.
Yeah.
98. 3 liters to centimeters cubed. So 3 liters. So first of all, look at the liters. 1 liter equals 1,000 centimeters cubed. So 1,000 centimeters cubed, 1 liter, which cancels the liters, and that's it. So 3,000. So 3,000. But there was more to it than that. That was it. 99. Part of a glacier that contains 80 cubic meters of ice breaks off and falls in the ocean. When the ice that has fallen into the ocean melts, determine the approximate amount of water in kiloliters obtained from the ice. Well, 1 cubic meter is 1 kiloliter. So it's a 1-to-1 again. So it's 80 kiloliters.
I like when they put the little graph right there.
But
Right?
what's that?
I like when they put the little graph right there, it just makes it easier.
Yeah, well, you have it here too.
Mm-hmm.
You don't have, yeah, you have all of them that they have. Yeah. It's from the book too, just so you know. For some reason, I have this one on here too. Okay, so we don't want to watch the video. Find the volume of a rectangular shipping container. So they're all meters, right?
Mhm.
Boom, boom, boom. So I'll have to worry about the dimension. It'll be meters cubed. And so it's 8 times 18, 18 times 8 times 3. And that's 432 cubic meters. The next part of the question is, I think, is there another part? What happened?
That's the last one.
Yep.
That's it.
Yeah.
All right, so you're armed for homework 4, and we'll do homework 5 on Thursday. Are there any questions?
No.
No?